So here's something worth thinking about as you settle in tonight. Right now, at this very moment, your body is doing something extraordinary without asking your permission. Your heart is beating somewhere around 60 to 80 times a minute, and each of those beats involves a cascade of electrical impulses and muscle contractions that, every once in a while, just by pure chance, could misfire. But it almost never does. The odds of any single heartbeat going wrong in a healthy person are vanishingly small. And yet, over the course of a lifetime, your heart will beat roughly 2.5 billion times. 2.5 billion chances for something to go sideways. And somehow, for most of us, the math works out. The overwhelming probability of each beat being fine, multiplied across billions of repetitions, adds up to a life. That's probability. That's the quiet mathematics running underneath everything you do, everything you are, every moment of every day. And the strange thing is, for most of human history, nobody had any real framework for thinking about it. That's what we're going to talk about tonight. Probability. The mathematics of chance, of uncertainty, of not knowing what happens next, but having a surprisingly powerful way to reason about it anyway. We're going to take it slow, start way back at the beginning, and just walk through it together. No rush. If you drift off somewhere along the way, that's perfectly fine. The ideas will still be here. And honestly, probability is one of those subjects that settles into your mind beautifully when you're relaxed and unhurried, when you're not trying to memorize formulas but just letting the logic of it wash over you. Because the ideas themselves are surprisingly intuitive, even when the results are shocking. And some of the results, as you'll see, are genuinely shocking. Let's start with something that might surprise you, which is just how late humanity figured this out. We're talking about one of the most practically useful branches of mathematics ever developed. Something that today underpins everything from weather forecasting to medical diagnosis, to the insurance policy on your car, to the algorithm deciding what shows up in your social media feed. And it essentially didn't exist as a formal discipline until the middle of the 17th century, the 1650s. That's shockingly recent. Humans had been doing geometry for thousands of years. The Babylonians were solving quadratic equations around 2000 BCE. The Greeks had Euclid and his Elements around 300 BCE, a work so perfectly structured that Abraham Lincoln supposedly studied it to sharpen his logical thinking. Algebra, trigonometry, calculus. All of these came before anyone sat down and worked out the basic rules of probability in any systematic way. Think about that. We figured out how to calculate the areas of circles and the volumes of spheres 2,000 years before we figured out how to reason rigorously about the odds of rolling a 7 with 2 dice. That's a strange gap in human knowledge, and the reasons for it are genuinely fascinating. Because it's not that people didn't encounter randomness. Of course they did. They encountered it constantly. Humans have been gambling for at least 5,000 years. Archaeologists have found dice, actual 6-sided dice, looking remarkably similar to the ones you might have in a board game in your closet right now, in Mesopotamian sites dating back to around 3000 BCE. Some of the earliest ones were made from the ankle bones of sheep, called astragali, which have 4 flat sides and were used as randomizing devices across the ancient world. The ancient Egyptians played a board game called senet that involved throwing sticks as a randomizing device. The Romans were absolutely obsessed with dice games. The Emperor Augustus wrote in his letters about his gambling losses and wins. And the Emperor Claudius reportedly wrote an entire book about how to win at dice, which has unfortunately been lost to history. People have been rolling dice, flipping coins, drawing lots, and betting on outcomes since the dawn of civilization. They knew perfectly well that some outcomes were more likely than others. A Roman gambler could tell you that rolling a pair of 6s was harder than rolling a 7 with 2 dice. They had an intuitive sense of the odds. They just never wrote down the rules. And the reasons for that delay are debated by historians, but a few things seem to have gotten in the way. One was the pervasive belief in many ancient cultures that random events weren't actually random at all. They were expressions of divine will. When you cast lots, you weren't sampling from a probability distribution. You were asking the gods to speak. The outcome of a dice throw wasn't governed by mathematics. It was governed by fate, or fortune, or the whims of some deity. The Romans had a goddess of fortune, Fortuna, who was depicted with a wheel that she spun to determine human destinies. The Greeks had the Moirai, the three fates, who spun and measured and cut the thread of each person's life. If that's how you understand randomness, as the voice of the divine, then there's no reason to develop a mathematical theory of it. You don't calculate the will of the gods. You accept it, or you try to appease the gods, or read the signs, or perform the right rituals. But you don't sit down with a quill and parchment and start counting outcomes. There's actually a wonderful example of this in the Bible. In the book of Proverbs, chapter 16, verse 33, it says, and I'm paraphrasing here, "The lot is cast, but every decision is from the Lord." That captures the ancient attitude perfectly. The mechanism might look random, but the outcome is predetermined by a higher power. And that mindset, that theological framing of randomness, persisted for a remarkably long time. Even well into the Middle Ages, the idea that chance events followed mathematical laws would have struck most people as borderline blasphemous. You're trying to put God's decisions into an equation? That doesn't sit right. So the mathematics of probability had to wait for a cultural shift, a shift toward seeing the world as governed by natural laws that could be discovered and described, rather than by inscrutable divine intentions. And it also had to wait for someone who was both mathematically gifted and deeply, personally invested in the outcomes of random events. Someone who gambled a lot. Someone whose losses kept him up at night, whose debts followed him from city to city, but whose mind was sharp enough to see patterns in the chaos. And that brings us to one of the most colorful characters in the entire history of mathematics, Girolamo Cardano. Born in 1501 in Pavia, Italy, Cardano was, depending on who you ask, either a genius polymath or an absolute disaster of a human being. He was probably both. His life reads like a novel that you'd put down because the plot was too implausible. He was an illegitimate child. His father was a mathematically gifted lawyer who was friends with Leonardo da Vinci, and his mother reportedly tried to abort him before he was born. He grew up sickly, afflicted by what he described as a variety of ailments throughout his childhood. But he was brilliant, and he fought his way into medical school, eventually becoming one of the most sought-after physicians in all of Europe. He once traveled to Scotland to treat the Archbishop of St. Andrews for chronic asthma, and apparently cured him by removing the feather pillows from his bedroom, which, if the Archbishop was allergic to feathers, was actually a perfectly sensible medical intervention. Cardano was also a mathematician who made fundamental contributions to algebra. He published the first general solutions to cubic and quartic equations, though the story behind that involves a bitter priority dispute with another mathematician named Niccolò Tartaglia that makes academic rivalries today look tame. He wrote over 200 works on subjects ranging from medicine to philosophy to astrology to music to dreams. And he was a compulsive gambler who spent large portions of his life broke, in debt, and in trouble. He gambled on cards, dice, chess, anything with an uncertain outcome. He once pawned his wife's jewelry to cover gambling debts. He was, by his own admission in his autobiography, unable to stop. Here's the thing about Cardano, though. He couldn't stop gambling, but he was also brilliant enough to notice patterns in his losses, and around the 1560s, He wrote a book called Liber de Ludo Aleae, the book on games of chance. It wasn't published until 1663, long after his death, and by then, the real founders of probability theory had already done their work independently. But Cardano's book is remarkable because it contains the first serious attempt to analyze random events mathematically. He understood the basic idea of counting favorable outcomes versus total possible outcomes. He knew that the probability of rolling a 6 on a fair die was 1 in 6, one favorable outcome out of 6 equally likely possibilities. He discussed the probabilities of various dice combinations. He even had a rough version of what we'd now call the law of large numbers, the insight that the more times you repeat a random experiment, the closer the observed frequencies get to the theoretical probabilities. He wrote something to the effect that the nature of the die is such that in the long run, each face comes up an equal number of times. And there's a wonderful honesty in Cardano's writing about gambling. He described the psychological traps that gamblers fall into, the belief that luck runs in streaks, the temptation to chase losses, the seductive feeling that you're due for a win. He knew these were errors of reasoning, even though he couldn't stop himself from making them. He was, in a sense, the first person to simultaneously understand probability and be terrible at acting on that understanding, which, if you think about it, is a very human combination. But Cardano's life was genuinely tragic in a way that's hard to shake off. His eldest son, Giambattista, was executed for murder in 1560. He'd poisoned his wife after learning she'd been unfaithful. His younger son was a gambler and a thief who caused Cardano endless grief and apparently informed on his own father to the Inquisition. Cardano himself was arrested by the Inquisition in 1570, likely for casting the horoscope of Jesus Christ, which was considered heretical. He spent a brief time in prison, was released, and spent the last few years of his life in Rome under a kind of house arrest, sustained by a pension from the Pope of all things. He died in 1576. There's a legend, probably invented, but characteristically dramatic, that he predicted the date of his own death using astrology, and when the day arrived and he was still alive and healthy, he killed himself to preserve his prediction. That almost certainly didn't happen. But the fact that people told that story about him tells you something about the kind of figure he was. So Cardano planted a seed, but the flower didn't bloom until 1654, when two of the greatest mathematical minds in France exchanged a series of letters that would change mathematics forever, and the whole thing started because of a gambler's question. Which is perfect, really. The most important intellectual correspondence in the history of probability theory was prompted by a guy who wanted to know if his bet was fair. The gambler's name was Antoine Gombaut, but he went by the title Chevalier de Marais, and he fancied himself a man of sophisticated taste and sharp logical thinking. He had noticed something puzzling about two different dice games he played. In the first game, you roll a single die 4 times and bet on getting at least 1 6. The Chevalier knew from experience that this was a slightly favorable bet. Over many games, you'd win more often than you'd lose. In the second game, you roll a pair of dice 24 times and bet on getting at least 1 double 6. The Chevalier had reasoned that since a double 6 is 6 times less likely than a single 6, you'd need 6 times as many rolls to have the same odds, which would be 24. So the second game should be just as good as the first. But when he played the second game, he kept losing. Not every time, but more often than he won. Something was wrong with his reasoning, and he couldn't figure out what. So he brought the puzzle to his friend Blaise Pascal. Pascal was 31 years old in 1654, already famous as a mathematician and physicist. He'd built a mechanical calculator as a teenager, the Pascaline, one of the first in the world, designed to help his father, a tax commissioner, with the tedious arithmetic of his job. He'd done groundbreaking work on the physics of fluids and pressure. the unit of pressure, the Pascal, is named after him. He was also increasingly drawn to religion, pulled toward the austere Christianity of the Jansenist movement, and within a few years he would abandon mathematics almost entirely to devote himself to theology and write the Pensées, one of the masterpieces of French literature. But in 1654, he was still doing math, and the Chevalier de Méret's puzzle caught his attention. The resolution, by the way, is a beautiful illustration of why intuition fails in probability. The Chevalier's reasoning, that 24 rolls of 2 dice should give you the same odds of a double 6 as 4 rolls of 1 die give you for a single 6, sounds logical, but is subtly wrong. The probability of not rolling a 6 in a single throw is 5/6. The probability of not rolling a 6 in 4 throws is 5/6 multiplied by itself 4 times, which is about 0.482. So the probability of getting at least 1 6 in 4 throws is about 0.518, a little better than even, just as the Chevalier had observed. But for double 6s, the probability of not rolling a double 6 in a single throw of 2 dice is 35 out of 36. Multiply that by itself 24 times, and you get about 0.509. So the probability of getting at least 1 double 6 in 24 throws is only about 0.491, just under 50%. The Chevalier's bet was a losing one, by a slim margin. The error in his reasoning was assuming that probabilities scale linearly, that you can just multiply the number of trials. They don't. They compound, and compounding works differently. But the Chevalier's puzzle was just the appetizer. The main course, the problem that really birthed probability theory, was something called the problem of points, and it goes like this. 2 players are playing a game of chance, say, flipping a coin. They've agreed that the first one to win a certain number of rounds takes the whole pot. But the game gets interrupted partway through, before either player has reached the target. The question is, how should the pot be divided fairly, not equally, fairly, based on how likely each player is to win if the game were to continue? Think about that for a second. Say you and I are flipping a coin, and we agree that the first to win 3 flips takes the prize. I'm ahead 2-1 when we have to stop. We can't keep playing. How do we split the money? You might think, well, I was ahead 2-1, so take 2/3 and give you 1/3. But that's not right, because it doesn't account for the actual probabilities. If we'd kept playing, I'd only need 1 more win, while you'd need 2 more. Working that out precisely, figuring out exactly how to weight the remaining possible outcomes, is a genuinely subtle problem, and it had stumped people for centuries. The Italian mathematician Luca Pacioli had written about it in 1494 and got it wrong. Tartaglia, Cardano's rival, had written about it and also gotten it wrong. The problem was slippery, and until Pascal came along, nobody had nailed it down. Pascal didn't solve it alone. He wrote to Pierre de Fermat, a lawyer and magistrate in Toulouse, who happened to be one of the greatest mathematicians of the age. Some would say the greatest amateur mathematician who ever lived, since mathematics was never his profession. Fermat spent his days judging legal cases and his evenings doing mathematics of the highest order. He's famous today mostly for Fermat's last theorem, that tantalizing marginal note where he claimed to have found a proof that the equation x to the n plus y to the n equals z to the n has no whole number solutions when n is greater than 2, but the margin of his book was too small to contain the proof. That marginal note tormented mathematicians for over 350 years, until Andrew Wiles finally proved it in 1995, using mathematics that Fermat couldn't possibly have known. Whether Fermat actually had a proof, or just thought he did, is one of the great unsolved questions in the history of mathematics. But regardless, Fermat was a genius, And he was exactly the right person for Pascal to consult about probability. The exchange of letters between Pascal and Fermat in the summer of 1654 is one of the founding documents of probability theory. They approached the problem of points from different angles. Fermat used direct enumeration, essentially listing out all the possible ways the remaining game could unfold and counting the favorable outcomes for each player, while Pascal developed a more recursive approach, working backward from the end of the game. But they arrived at the same answers, and in doing so, they established something profound: the idea that future uncertainty can be quantified precisely, that you can reason rigorously about events that haven't happened yet, that you can assign a number to the likelihood of something occurring, and that number means something real and defensible. It's not a guess, it's not a hunch, it's a calculation as reliable as any other piece of mathematics. Here's what's really beautiful about what they did. They took uncertainty, this thing that had always felt irreducibly fuzzy, the domain of gut feelings and superstition and gambling lore, and they tamed it. They showed that probability follows rules, just like geometry follows rules, just like algebra follows rules. And once you know the rules, you can compute, you can predict, you can make decisions that are grounded in something more solid than instinct. Pascal, in particular, went further than just solving the Chevalier's puzzles. He developed what we now call Pascal's triangle, although, to be fair, the triangle had been discovered independently by Chinese mathematicians as far back as the 11th century, and by Persian mathematicians around the same time. But Pascal used it more systematically than anyone before him. Pascal's triangle is a beautiful thing. Each number is the sum of the two numbers above it, and it generates the binomial coefficients, the numbers that tell you how many ways a certain combination of outcomes can occur. If you flip a coin 10 times, how many ways can you get exactly 6 heads? Pascal's triangle gives you the answer: 210. And that number, divided by the total number of possible outcomes, which is 2 to the 10th, or 1024, gives you the probability. It's a simple, elegant structure that encodes an enormous amount of combinatorial information, and it's directly connected to probability, because once you know how many ways something can happen and how many things could happen in total, you can compute how likely it is. And then Pascal did something else, something that takes us slightly sideways from pure mathematics, but is too interesting to skip. He made a probabilistic argument about God, Pascal's wager. You've probably heard of it. The idea is this: you don't know whether God exists, but you can think about it as a kind of bet. If you believe in God and you're right, you gain everything: eternal salvation. If you believe and you're wrong, you lose relatively little. If you don't believe and you're right, you gain relatively little. But if you don't believe and you're wrong, you lose everything: eternal damnation. So when you multiply the probability of each outcome by its payoff and compare the options, the rational bet is to believe. Now, this argument has been picked apart by philosophers for 3.5 centuries, and there are excellent objections to it. Which God? What if the wrong belief is worse than no belief? Does it even count as genuine belief if you're just placing a calculated bet? All valid. But what's important for our purposes is the structure of the reasoning. Pascal was using expected value, the probability of an outcome multiplied by its payoff, to reason about a decision under uncertainty. And expected value would become one of the most powerful and pervasive concepts in all of probability theory. It's how insurance companies set premiums. It's how investors evaluate portfolios. It's how engineers decide which safety margins to build into bridges and buildings. It's how game designers balance rewards and risks. Every time someone weighs the odds of something happening against how good or bad it would be if it did, They're using the basic logic that Pascal articulated in the 1650s. So by the time Pascal died in 1662, young, only 39, his body ravaged by the chronic illness that had plagued him since childhood, the foundations of probability theory had been laid. The key ideas were there: counting outcomes, computing ratios, using those ratios to make decisions. But the theory was still rough, still limited to simple games with clear rules and finite possibilities. The real world is messier than that. Coins don't always have exactly two sides of equal weight. Dice aren't always perfectly balanced. Outcomes aren't always equally likely. And the number of possible outcomes isn't always something you can sit down and count on your fingers or even on a page. To handle that messiness, probability theory needed to grow up. It needed new tools, deeper ideas, a way to handle not just what might happen on a single roll, but what tends to happen across thousands and millions of repetitions. And the person who took that crucial next step was a member of what might be the most mathematically talented family in history, the Bernoullis. This family, originally from Basel, Switzerland, refugees from the Spanish Netherlands who settled in Switzerland to escape religious persecution, produced at least 8 prominent mathematicians across 3 generations, which is genuinely absurd when you think about it. The probability of one family producing that much mathematical genius is, well, astronomically small. They were also, by many accounts, a family rife with jealousy, rivalry, and petty disputes. Jacob Bernoulli and his younger brother Johann were both brilliant, both prickly, and their relationship deteriorated into open hostility. Johann once submitted a mathematical problem to a journal and then published his own solution, which turned out to have been plagiarized from his son Daniel's work. Jacob and Johann publicly attacked each other's mathematics. It was academic dysfunction at its finest, but the mathematics they produced was extraordinary. And Jacob Bernoulli is the one who matters most for our story. Born in 1655, he was the eldest of the mathematical Bernoullis, and he spent over 20 years working on a book that he never finished in his lifetime. It was published posthumously in 1713, 8 years after his death, under the title Ars Conjectandi, the art of conjecturing, and it contains one of the most important results in all of mathematics. Here's the big idea, and it's one of those things that sounds simple, but gets deeper and deeper the longer you sit with it. Suppose you have a coin, and you don't know whether it's fair. Maybe it's slightly weighted, maybe one side is a little heavier, maybe the edge is shaved just a tiny bit. You can't just assume the probability of heads is 1/2, because you don't know that. So what do? You flip it, a lot, and you watch what happens. If you flip it 100 times and get 53 heads, that tells you something. If you flip it 1,000 times and get 512 heads, that tells you more. And if you flip it 10,000 times and get 5,021 heads, you're getting a very precise estimate that the true probability of heads is very close to 1/2. This is the law of large numbers, and Jacob Bernoulli proved it rigorously, the first person ever to do so. It says, essentially, that as you increase the number of independent trials of a random experiment, the observed frequency of any particular outcome converges to its true underlying probability. The more data you gather, the closer your estimate gets to the truth. And you can make the estimate as accurate as you want. You just need enough trials. Bernoulli even worked out how many trials you'd need for a given level of confidence. Though the number he got was impractically large, he calculated that for a particular example, you'd need over 25,000 trials, which disappointed him. Think about what a profound statement this is. It's saying that randomness, given enough repetition, becomes predictable. Each individual coin flip is uncertain. You genuinely don't know whether it'll be heads or tails. But 1,000,000 coin flips? That's almost perfectly predictable. You'll get very close to 500,000 heads. Not exactly that number, probably, but close. Very, very close. The randomness of the individual events gets smoothed out by the sheer volume of repetition, and what emerges is a stable, reliable pattern. Chaos at the micro level, order at the macro level. It's one of the most beautiful ideas in all of mathematics. This is why casinos always win in the long run. Not on every hand, not on every spin. Any individual gambler might walk away rich on any given night. But across millions of bets, across thousands of players, across months and years, the small mathematical edge that the house has on every game, a few percentage points, sometimes less, translates, with near certainty, into a predictable, reliable profit. The law of large numbers is the casino's best friend. It's the reason the house always wins. Not because of luck, not because of cheating, but because of mathematics. Cardano would have appreciated the irony. He understood the theory, but couldn't resist playing against the odds anyway. And here's where I want to introduce you to one of those ideas that seems simple at first, but gets deeper the longer you sit with it. Because the law of large numbers tells you that averages stabilize as you gather more data. But it doesn't tell you how they stabilize. It doesn't describe the shape of the variation along the way. It doesn't tell you what the scatter looks like before it settles down. For that, you need another idea. One that would be developed by a French mathematician living in England. A man with a somewhat melancholy life, who discovered one of the most important and universal shapes in all of science. Abraham de Moivre was born in 1667 in Vitry-le-François, in the Champagne region of France. He was a Huguenot, a French Protestant, and when Louis XIV revoked the Edict of Nantes in 1685, making Protestantism effectively illegal in France, de Moivre's world fell apart. Thousands of Huguenots were imprisoned. De Moivre himself may have spent time in prison before fleeing to London. He would spend the rest of his life there, and he would never go back. In England, he found intellectual companionship. Isaac Newton himself admired de Moivre's mathematical abilities, and reportedly said, when people came to him with mathematical questions, "Go to Mr. de Moivre. He knows these things better than I do." Whether Newton actually said that, or it's a polished anecdote, is hard to say, but it captures the respect de Moivre commanded among the mathematical elite. And yet, despite this, de Moivre never obtained a university professorship. He was a foreigner in England, a refugee, and the academic establishment never quite made room for him. He made his living by tutoring wealthy students and consulting on probability problems for gamblers and insurance underwriters, often meeting clients in Slater's coffee house in the city. There's something poignant about that. One of the great mathematical minds of the 18th century, spending his days in a coffee house, working out odds for paying customers, because no university would give him a permanent position. He died in 1754, at the age of 87, reportedly predicting his own death by noting that he was sleeping 15 minutes longer each day and calculating when the progression would reach 24 hours. But de Moivre's contribution to probability was monumental. Here's what he discovered, and it's something you encounter every single day, even if you've never heard his name. Suppose you flip a coin a large number of times, say 100, and you count how many heads you get. You know from Bernoulli's work that the average should be close to 50, but it won't be exactly 50 every time. Sometimes you'll get 47, sometimes 53, occasionally 60, rarely 38. If you repeated this entire experiment many, many times, flip 100 coins, count the heads, write down the number, start over, flip another 100, count again, thousands and thousands of times, and then you drew a graph showing how often each count came up, you'd get a shape. And that shape, de Moivre discovered around 1733, is a bell curve, smooth, symmetrical, highest in the middle, tapering off on both sides in that distinctive, graceful way. The most likely result is right at the center, 50 heads, and the further you get from 50 in either direction, the less likely that result becomes. But it doesn't drop off linearly or sharply. It follows a very specific mathematical curve, what we now call the normal distribution, or the Gaussian distribution, named after Carl Friedrich Gauss, the great German mathematician who studied it extensively, about 70 years after de Moivre first described it. Gauss used it to analyze errors in astronomical observations, and his work on it was so influential that the bell curve is often called the Gaussian distribution, even though de Moivre got there first. Mathematical naming conventions aren't always fair. And here's what's wild about the bell curve. It doesn't just show up in coin flips. It shows up everywhere. Measure the heights of 1,000 adult men in a given population, and the distribution will be approximately bell-shaped. Measure the errors in repeated laboratory observations of the same quantity, the position of a star through a telescope, the weight of a bag of flour on a scale, the length of a machined part rolling off an assembly line, and the errors follow a bell curve. Blood pressure readings across a population, the scores on a standardized test, the annual returns of a diversified stock portfolio, the velocities of gas molecules at a given temperature, the tiny variations in the diameter of manufactured ball bearings. All of these, under the right conditions, produce distributions that look like that same smooth, symmetrical, bell-shaped curve. Why? What is it about the bell curve that makes it so universal? The deep answer, and it really is deep, one of the most remarkable convergence results in all of mathematics, came from something called the central limit theorem. This wasn't a single discovery, but rather a result that was developed, refined, and generalized over more than a century by a succession of brilliant mathematicians. Laplace made the first major progress, then Poisson extended it, then Chebyshev and his students Markov and Lyapunov put it on a rigorous footing in the late 19th and early 20th centuries. And what the central limit theorem says is something extraordinary. It says that whenever you have a quantity that's the result of adding up many small, independent random contributions, the distribution of that total will tend toward a bell curve, regardless of the distribution of the individual contributions. Regardless. That's the key word. It doesn't matter if the individual random factors follow a uniform distribution, a skewed distribution, a lumpy distribution, or some weird shape with no name. As long as you're adding up enough of them, and none of them is so large that it dominates the sum, the total converges to a normal distribution. It's not an approximation that gets better slowly. It converges with remarkable speed. Even 20 or 30 independent random variables, added together, often produce a sum that looks almost perfectly bell-shaped. Think about what that means for something like human height. Your height is determined by the combined effect of hundreds of genes, each contributing a small amount to your final stature, plus a collection of environmental factors, nutrition during childhood, overall health, physical activity, each contributing a small amount. None of these factors single-handedly determines how tall you are. Your height is the sum of many small, roughly independent influences, and so the distribution of height across a population is bell-shaped, not because there's some deep biological law mandating that heights must follow a normal distribution, but because any time you add up a lot of small independent things, you get a bell curve. It's a mathematical inevitability. The central limit theorem guarantees it. That's the central limit theorem, and it might be the single most important result in all of statistics. It's the reason the bell curve is everywhere. It's the reason your doctor can talk about normal ranges for blood tests. Those ranges are defined using the statistics of the normal distribution. It's the reason quality control engineers can predict how many defective parts will come off an assembly line. It's the reason pollsters can estimate the margin of error in an election survey. Underneath all of these applications is the same deep mathematical truth. When many small random effects combine, the bell curve emerges. Randomness has a universal shape, and that shape is the bell. There's something almost comforting about that, isn't there? All the chaos and unpredictability of individual random events, all the noise and mess and uncertainty, and underneath it all, this serene, stable, mathematically precise form, just waiting to emerge if you step back far enough and collect enough data. The bell curve is what randomness looks like from a distance. Up close, everything is noise. From far away, everything is a bell. Now, while the mathematics of probability was developing along these lines, counting outcomes, the law of large numbers, the bell curve, the central limit theorem, there was another thread developing quietly alongside it. A different way of thinking about probability entirely. Not probability as counting, not probability as long-run frequency, but probability as a way of updating your beliefs when you get new evidence. And this thread starts with a man you've probably never heard of, a man who published almost nothing in his lifetime, whose most important idea was presented to the world by a friend after his death. His name was Thomas Bayes, and his contribution would spark a philosophical argument about the very meaning of probability that continues to this day. Thomas Bayes was born around 1701 in London, the son of one of the first nonconformist ministers to be ordained in England after the Act of Toleration in 1689. He became a minister himself, serving a Presbyterian congregation in Tunbridge Wells, a pleasant spa town in Kent, about 35 miles southeast of London. He was apparently a capable mathematician. He was elected a Fellow of the Royal Society in 1742, which was a significant honor, but he published very little during his lifetime. Just 2 known works, one of them a theological tract. He seems to have been quiet, modest, perhaps the kind of person who thinks deeply about things but doesn't feel a burning need to announce his conclusions to the world. He died in 1761, and his papers were passed to a friend, a man named Richard Price, who found among them an essay on what Bayes called the doctrine of chances. Price recognized the importance of what Bayes had done, edited the work, and presented it to the Royal Society in 1763 under the title An Essay Toward Solving a Problem in the Doctrine of Chances. It's now known as Bayes' theorem, and it's one of the most important and most argued about results in the entire history of mathematics. Here's the basic idea, stripped down to its essence. The probability we talked about before, the Pascal-Fermat-Bernoulli kind, typically starts with a known setup and asks what outcomes to expect. You know the coin is fair. What's the probability of getting 7 heads in 10 flips? You know the die is honest. What's the probability of rolling a sum of 9 with 2 dice? You start with the model and predict the data. This is sometimes called forward probability. Bayes turned it around. He asked, what if you have the data and you want to figure out the model? You've flipped a coin 10 times and gotten 7 heads. What can you now say about the coin? Is it fair? Is it weighted? How confident should you be? You've seen a patient with certain symptoms. What's the probability that they have a particular disease, given what you've observed? This is inverse probability, reasoning backward from effects to causes, and it turns out to be far more subtle and far more powerful than forward probability. Bayes' theorem provides the machinery. It says that the probability of a hypothesis, given the evidence, equals the probability of the evidence given the hypothesis, multiplied by the prior probability of the hypothesis, divided by the total probability of the evidence. That's a mouthful, so let me walk you through an example that makes it vivid. Because this example, once you understand it, changes the way you think about medical testing, forensic evidence, and a whole lot of other things you encounter in everyday life. Suppose there's a rare disease that affects 1 person in 1,000, and there's a test for it. A good test, 99% accurate. If you have the disease, the test correctly says positive 99% of the time. If you don't have the disease, the test correctly says negative 99% of the time. You take the test. It comes back positive. What's the probability you actually have the disease? Most people, including most doctors, disturbingly, instinctively say 99%. The test is 99% accurate, so there's a 99% chance the result is right. But that's wrong. That's dramatically, dangerously wrong. Let's work through it. Imagine 10,000 people taking the test. On average, 10 of them actually have the disease, because it affects 1 person in 1,000. Of those 10, the test correctly identifies about 10, let's say all 10, for simplicity. So 10 true positives. Now, of the remaining 9,990 people who don't have the disease, the test gives a false positive 1% of the time. 1% of 9,990 is about 100, so you have roughly 100 false positives. That means about 110 people total test positive, 10 who really have the disease and 100 who don't. So if you're one of the people who tested positive, the probability that you actually have the disease is 10 out of 110. That's about 9%, not 99, 9. Let that sink in for a second. A 99% accurate test, applied to a rare disease, and a positive result, still means there's a 91% chance you're fine. The reason is the base rate, the prior probability. The disease is so rare that even a highly accurate test generates far more false positives than true positives, simply because there are so many more healthy people being tested than sick ones. The prior probability, 1 in 1,000, acts as a massive anchor, and a single positive test result, even from an excellent test, only moves the needle so far. This has enormous practical consequences. It's why screening programs for rare conditions can generate floods of false positives, leading to unnecessary anxiety, invasive follow-up procedures, and sometimes even harmful treatments for diseases the patient never had. It's why a second independent test is so valuable, because a second positive result updates your probability dramatically, since the base rate for the second test is no longer 1 in 1,000, but rather about 9%. A second positive pushes the probability much higher. The Bayesian update builds on itself. And this kind of reasoning extends far beyond medicine. In criminal justice, even highly accurate forensic evidence, DNA matching, fingerprint analysis, ballistics testing, can be misleading if the prior probability of guilt is very low. If you test a random person's DNA against a crime scene sample and get a match, and the test has a false positive rate of 1 in a million, that sounds incredibly damning. But if the suspect was selected from a city of 10 million people, then you'd expect about 10 false matches in the city. So the DNA match alone doesn't prove guilt. It makes the suspect one of perhaps 11 people, 10 of whom are innocent, who would have matched. The prior matters. Where you start matters. Bayes understood this in the 1750s, and we're still trying to get courts and doctors and policymakers to understand it today. Now, Bayes himself might not have fully grasped the reach of his idea. His essay was modest, focused on a specific mathematical problem. It was Pierre-Simon Laplace, the great French mathematician and astronomer, who really ran with Bayesian thinking and turned it into a sweeping philosophical framework. Laplace was born in 1749 in Normandy. the son of a cider merchant, a modest background that makes his eventual rise to the pinnacle of French science all the more remarkable. Through sheer brilliance, tireless work, and a fair amount of political savvy, Laplace managed to survive the French Revolution, the Reign of Terror, Napoleon's rise and fall, and the Bourbon Restoration, all while remaining near the top of the scientific establishment, which required some impressive political nimbleness. He's sometimes called the French Newton, and with good reason. His Mécanique Céleste was a monumental 5-volume work that reformulated Newton's gravitational theory using advanced mathematics, essentially showing that the observed motions of every planet, moon, and comet in the solar system could be explained by gravitational theory alone, without needing to invoke any divine intervention to keep things stable. And that phrase, without divine intervention, captures something important about Laplace. There's a famous story, probably embellished but too good not to tell, that when Napoleon asked Laplace why his great book on celestial mechanics made no mention of God, Laplace replied, "Sire, I had no need of that hypothesis." Whether he actually said those exact words or not, the anecdote captures his worldview perfectly. Laplace was a determinist. He believed the universe was a vast machine, running according to fixed laws, and that if some supreme intelligence, some imaginary being, knew the precise position and velocity of every particle in the universe at a single instant, that being could, in principle, calculate the entire future and reconstruct the entire past. This hypothetical all-knowing calculator is called Laplace's demon, and it's one of the most famous thought experiments in the philosophy of science. But here's the key insight, the thing that connects Laplace to our story about probability. Laplace recognized that real beings, actual humans, as opposed to imaginary demons, are profoundly ignorant. We don't know the positions of all the particles. We can't track every variable. We are, fundamentally, uncertain about almost everything, and probability, for Laplace, was not a property of the physical world. It was a measure of our own ignorance. When we say there's a 50% chance of heads, we're not saying something about the coin. The coin, if we knew its exact initial velocity, its spin, the air resistance, the distance to the table, would land on a perfectly deterministic side every time. We're saying something about us. We don't know all those details, and our ignorance is symmetric, so we assign equal probabilities to heads and tails. This is a deeply philosophical position, and it puts Laplace squarely in the camp of what we'd now call the subjectivist or Bayesian interpretation of probability. Probability isn't out there in the world. It's in here, in the mind. It's about what you know and what you don't know about the world. It's about rational belief in the face of uncertainty, and different people with different information can rationally assign different probabilities to the same event. That's not a weakness of the framework. That's the whole point. An insurance actuary who has studied your medical records assigns a different probability to your having a heart attack than your friend who's never seen them. Both probabilities are valid, given their respective knowledge. Neither is right in some absolute sense. They're both rational summaries of what each person knows. Now, this Bayesian interpretation would eventually come into fierce conflict with a rival view, the frequentist interpretation, which says that probability is about long-run frequencies of repeatable events, period. The probability of heads is 1/2, because if you flip a coin a huge number of times, heads will come up about half the time. End of story. Probability is an objective property of a repeatable process, not a subjective degree of belief. And the battle between Bayesians and frequentists would rage through the entire 20th century, sometimes with genuine acrimony, shaping the development of statistics, science, and public policy in ways that affect your life today. But we'll come back to that battle in a bit. Right now, I want to take a different turn, because this is a good moment to talk about something more human. Something about how we actually think about probability in practice, which turns out to be very different from how we should think about it. Because here's the uncomfortable truth. Human beings are terrible at probability, not just occasionally confused by tricky problems. Systematically, predictably, almost comically bad at it. Our brains evolved to handle a world of concrete, immediate, physical experiences. Predators, food sources, social hierarchies, weather patterns. Not a world of abstract numerical reasoning about likelihood. And the result is that when it comes to probability, our intuitions mislead us in ways that are consistent, well-documented, and sometimes devastating in their consequences. Let me give you one of the most famous examples. On August 18, 1913, at the Monte Carlo Casino in Monaco, something remarkable happened at a roulette table. The ball landed on black, and then it landed on black again, and again, and again. After about 10 consecutive blacks, gamblers started noticing. After 15, they started crowding around the table, and they started piling money onto red, absolutely convinced that red was due. The run of blacks couldn't possibly continue, right? The wheel had to balance out. It was practically certain that red was coming next. People were pushing stacks of chips onto red, betting their evening's winnings, some reportedly borrowing money from friends and strangers alike, utterly certain that the streak had to end. The ball landed on black 26 times in a row, 26 consecutive blacks. The probability of that happening on a fair roulette wheel, where each spin is completely independent of every other spin, is roughly 1 in 67 million. An extraordinary event, certainly. But here's the thing, and this is the crucial point, the point that all those gamblers missed. The probability of black on the 27th spin was exactly what it had always been, a little under 50%, because of the green 0 and double 0 on the wheel. The roulette wheel has no memory. It doesn't know what happened on the previous spin. Each spin is an independent event, unaffected by every spin that came before it. The ball doesn't know it's been landing on black, and it's not trying to balance things out. The universe doesn't keep a ledger. It doesn't owe you a red. And yet, the gamblers at Monte Carlo that night behaved as if it did. They lost millions of francs, collectively, betting on what they felt certain was an overdue outcome. This is called the gambler's fallacy, and it's one of the most robust and widespread cognitive biases ever documented. People have an incredibly strong intuition that random sequences should look random at every scale, which they interpret as meaning that the sequences should balance out over short runs. If you've gotten 5 heads in a row, tails feels overdue. If your last 3 children were boys, a girl feels more likely this time. If a basketball player has missed his last 6 shots, he feels due to make the next one. But probability doesn't work that way. Each event is independent. The coin doesn't remember. The dice don't care. Now, here's where it gets subtle, and I want to take a moment with this, because the subtlety trips up even very smart people. The law of large numbers does say that, in the long run, the proportion of heads will converge to 50%. That's true. But it does this not by compensating for past imbalances, not by making up for a run of heads with extra tails, but simply by diluting them. If you've flipped 100 heads and 0 tails, you're at 100% heads. After another 10,000 flips, you'll have roughly 500 extra heads, half of 10,000, for a total of about 5,100 heads out of 10,100 flips. That's about 50.5%. The absolute imbalance, that original 100 extra heads, hasn't gone away. It's still there. But as a fraction of the total, it's become negligible. The past imbalance doesn't get corrected. It gets swamped by new data. And that distinction between correction and dilution is something most people never quite grasp intuitively. And speaking of intuition failures, let me tell you about one of the most delightful probability puzzles ever devised, the birthday paradox. Here's the question. How many people do you need in a room before there's a better than 50-50 chance that at least two of them share a birthday? Most people, when they hear this question for the first time, guess something large. Maybe 150, maybe 180. After all, there are 365 possible birthdays, ignoring leap days for simplicity. So surely you'd need a large fraction of that number to have a good shot at a match, right? The answer is 23, just 23 people. In a room of 23 randomly selected people, there's about a 50-50 chance that at least two of them share a birthday. By the time you get to 50 people, the probability is over 97%, and with 70 people, it's virtually certain, around 99.9%. Why is the number so shockingly small? Because we're not asking whether someone shares your specific birthday. That would indeed require a much larger group. You'd need about 253 people for a 50% chance of someone matching your particular birthday. We're asking a much broader question: whether any two people in the room share any birthday, and the number of possible pairs grows much, much faster than the number of people. With 23 people, there are 253 different pairs of people who could potentially share a birthday. That's 23 times 22, divided by 2. Each of those pairs is a separate, independent chance for a match, and those chances accumulate surprisingly quickly. The birthday paradox isn't really a paradox at all, of course. There's nothing logically contradictory about it. The math is perfectly straightforward. It's just deeply, reliably counterintuitive. Our brains aren't wired to think about combinatorial explosions, the way the number of possible combinations grows much faster than the number of elements. We think about the problem linearly. 23 people, 365 days. That's only about 6% of the days covered. How could there be a match? But we should be thinking about it quadratically. The number of pairs of people, which is what actually matters. And this failure of intuition shows up in practical contexts you'd never expect. In computer science, for instance, there's a class of security exploits called birthday attacks that rely on exactly this mathematical principle. If you're generating random cryptographic values, hash codes, session tokens, unique identifiers, you need far fewer of them than you'd intuitively expect before a collision occurs, before two values accidentally match. Systems that don't account for the birthday paradox can have surprisingly exploitable vulnerabilities. But perhaps no probability puzzle has generated more controversy, more furious letters, and more spectacularly wrong responses from people who should have known better than the Monty Hall problem. And the story of the Monty Hall problem is actually a story about something larger, about what happens when correct mathematical reasoning collides head-on with overwhelming human intuition, and intuition refuses to give ground. Here's the setup, based on the game show Let's Make a Deal, which was hosted by Monty Hall from 1963 to 1986. You're on the show. There are 3 doors. Behind one door is a car. Behind the other 2 are goats. You want the car. You pick a door. Say, door number 1. Now, the host, Monty Hall, who knows what's behind each door, opens one of the other 2 doors, always revealing a goat. He'll never open the door with the car. Say he opens door number 3 and shows you a goat. Then he asks, do you want to stick with your original choice, door number 1, or switch to the remaining unopened door, door number 2? Most people say it doesn't matter. There are 2 closed doors left, and the car is behind one of them. 50-50, right? Wrong. You should switch. Switching gives you a 2/3 chance of winning the car. Sticking gives you only 1/3. And if you find that hard to believe, if something in your gut is saying, that can't be right, you are in excellent, distinguished company. Because when Marilyn Vos Savant, who was listed in the Guinness Book of World Records for the highest recorded IQ, published this answer in her Parade magazine column in September 1990, she received approximately 10,000 letters, and nearly 1,000 of them came from people with PhDs. Many of the letters were condescending. Some were outright rude. One mathematician wrote, "You blew it, and you blew it big." Another, "You made a mistake, but look at the positive side." If all those PhDs were wrong, the country would be in some very serious trouble. They were certain she was wrong. She wasn't. She was right. And here's why. When you first picked door number 1, you had a 1 in 3 chance of being right. That means there was a 2/3 chance the car was behind one of the other 2 doors. Doors 2 and 3 combined. Now, Monty opens door number 3 and shows you a goat. This is crucial. Monty knows where the car is, and he would never open the door with the car. His action is not random. He's constrained. So his opening of door 3 doesn't change the probability that you were wrong initially. You still had a 1 in 3 chance of picking correctly, which means there's still a 2/3 chance the car is behind one of the other doors. But now one of those other doors, door 3, has been eliminated. So the entire 2/3 probability is concentrated on door 2. Switching gives you 2/3. Staying gives you 1/3. If you're still not fully convinced, and many people aren't, even after hearing the explanation, this is one of those problems where intellectual understanding and gut feeling refuse to reconcile. Try thinking about it with 1,000 doors. You pick one. Monty opens 998 others, all showing goats. 2 doors remain, yours and one other. Would you switch? Of course you would. Your door had a 1 in 1,000 chance. The other door has all the remaining probability concentrated on it. It's the same logic, just magnified to the point where your intuition finally agrees with the math. The Monty Hall problem became the most controversial mathematical puzzle of the 20th century, not because the math is complicated. It's actually quite simple once you set it up correctly, but because it exposed how powerfully our intuitions resist correct probabilistic reasoning. Even experts, even people who do mathematics for a living. The problem reveals something deep about human cognition. We tend to assess probabilities based on the current state of affairs. 2 doors, 1 car, that's 50-50, without properly accounting for the process that led to the current state. The history of the game, the rules that constrained Monty's choice, the information contained in his deliberate action. Our intuition doesn't naturally incorporate these things, and that failure of intuition has consequences far beyond game shows. This brings us to something fundamental. The systematic ways in which human reasoning fails at probability were catalogued most famously by 2 Israeli psychologists whose work would transform economics, medicine, public policy, and our understanding of the human mind itself. Their names were Daniel Kahneman and Amos Tversky, and starting in the early 1970s, they published a series of papers that are among the most cited in the entire social science literature. Kahneman would eventually win the Nobel Prize in Economics in 2002. Tversky, tragically, had died of metastatic melanoma in 1996 at the age of 59, and the Nobel is not awarded posthumously. What Kahneman and Tversky showed is that when people make judgments under uncertainty, when they estimate probabilities, assess risks, or predict outcomes, they don't do the math. They use mental shortcuts, which Kahneman and Tversky called, and these heuristics, while often useful and efficient in everyday life, lead to predictable, systematic errors, biases, in specific situations. One of the most powerful is the representativeness heuristic. People judge the probability of something by how well it matches a mental stereotype, a prototype. Here's their most famous example, which you might have encountered before. You're told that Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and she also participated in anti-nuclear demonstrations. Now, which is more likely? That Linda is a bank teller, or that Linda is a bank teller who is active in the feminist movement? Most people, something like 85% in experimental studies, say the second option is more likely. Linda as a feminist bank teller just fits the description better than Linda as just a bank teller. It's more representative. It makes a better story. But it's logically impossible for the second option to be more probable than the first. Think about it. Every feminist bank teller is also a bank teller. Bank teller and feminist is a subset of bank teller. A subset cannot be larger than the set that contains it. The probability of being both A and B can never exceed the probability of being just A. This error is called the conjunction fallacy, and the fact that most people make it, even after taking statistics courses, shows how deeply our judgments are driven by narrative coherence rather than logical structure. Then there's the availability heuristic. People estimate the probability of events based on how easily examples come to mind. Things that are vivid, recent, dramatic, or emotionally charged are easy to recall, so they feel more probable. This is why people consistently overestimate the risk of plane crashes and shark attacks and terrorist incidents. They're vivid and they dominate news coverage, while underestimating the risk of car accidents, heart disease, and diabetes, which are far more common but feel mundane and ordinary. After the September 11th attacks, thousands of Americans switched from flying to driving for their long-distance travel, because flying suddenly felt terrifyingly dangerous. But driving is, per mile, far more dangerous than flying. The extra driving in the months after September 11th led to an estimated 1,600 additional road deaths, more people than died in the attacks on the World Trade Center. The availability heuristic, amplified by fear and vivid imagery, caused people to make choices that were mathematically, demonstrably, more dangerous. Kahneman and Tversky's work was revolutionary because these weren't just random mistakes. They were systematic. They were predictable. They were wired into the architecture of human cognition, and they had real-world consequences in the way doctors assess patient risks, in the way juries weigh forensic evidence, in the way investors make financial decisions, in the way voters evaluate political claims. Understanding these biases, knowing where your own intuition is likely to fail, is one of the most practically valuable things you can learn about probability. It's not enough to know the math. You have to know where your brain will try to cheat on the math. But anyway, let's come back to the mathematical story, because while Kahneman and Tversky were documenting how people actually reason about probability, the mathematicians and statisticians were building the formal tools that probability should be reasoned with. And that story takes us through some of the most important intellectual developments of the 19th and 20th centuries: the building of modern statistics, the science of drawing conclusions from data. Let's talk about Francis Galton. Born in 1822 in Birmingham, England, into a wealthy and accomplished family, Charles Darwin was his half-cousin, which gives you a sense of the genetic lottery this family had won. Galton was one of those Victorian polymaths who seemed to be interested in absolutely everything. He explored uncharted regions of southern Africa in his 20s, publishing a popular account of his travels. He invented the weather map. Yes, someone had to invent it, and it was Galton, who figured out how to represent atmospheric pressure patterns graphically and recognized the rotating patterns of cyclones and anticyclones. He pioneered the use of fingerprints for identification, laying the groundwork for forensic fingerprint analysis that's still used today. He developed questionnaires and surveys as tools for scientific research. He even conducted a statistical study of the efficacy of prayer, which was bold by Victorian standards. Galton was also, it has to be said, a proponent of eugenics. He coined the term, in fact, and his ideas about the selective breeding of humans to improve the species are a genuinely dark chapter in the history of science. Those ideas, carried to their logical and horrifying extreme by others, would contribute to forced sterilization programs and, ultimately, to the ideology of the Nazi regime. Galton himself was no Nazi. He died in 1911, decades before the worst manifestations of eugenic thinking, but the scientific respectability he gave to the idea of ranking human fitness helped create an intellectual environment in which terrible things became possible. Science can be used for harm, and the story of eugenics is one of the starkest reminders of that truth. But Galton's contributions to statistical thinking were profound and lasting, and one of them was the discovery of a phenomenon that has been misunderstood more persistently and more consequentially than almost any other idea in statistics: regression to the mean. Here's what Galton noticed. He measured the heights of parents and their adult children, hundreds of families, carefully catalogued, and he found a fascinating pattern. Tall parents tended to have tall children, but not quite as tall as the parents. Short parents tended to have short children, but not quite as short as the parents. The children's heights moved, on average, toward the population mean, toward the center. He called this regression toward mediocrity, a phrase that's slightly unflattering, but mathematically precise. And he found the same pattern in other contexts. The size of sweet pea seeds from parent plants to offspring, for instance, showed the same tendency to regress toward the average. Now, here's where people go wrong, and they've been going wrong about this for over a century. The natural impulse is to think that regression to the mean is a causal force, some kind of biological or physical mechanism pulling extreme values back toward average, as if nature has a preference for mediocrity, a kind of gravitational pull toward the center. But that's not what's happening. Regression to the mean is a purely statistical phenomenon, and it appears any time you have imperfect correlation between two measurements. Here's a way to think about it that makes the mechanism clear. Suppose a student scores extraordinarily well on an exam. That score probably reflects two things: genuine ability, which is stable, and luck, random factors like which particular questions happen to appear, whether the student was feeling sharp that day, whether they happened to have just reviewed the right material the night before. The extreme score is partly signal and partly noise. When the same student takes the exam again, the signal, their ability, will still be there, but the noise, the lucky breaks, is unlikely to line up the same way. Sometimes the luck will be better, sometimes worse, but on average it'll be less extreme than whatever produced the outlier score. So the second score will tend to be lower, closer to the student's true average. Not because their ability has changed, not because some force is pulling them down, but because the lucky component of an extreme performance is, by definition, unlikely to repeat. This has enormous practical consequences, and the failure to understand it leads to errors that affect millions of people. Think about the sophomore slump in sports. A rookie athlete has an outstanding first season, wins awards, gets magazine covers. The next season, their performance drops. Sports commentators analyze the decline endlessly. Pressure, complacency, opponents figuring them out, off-field distractions. And sometimes those explanations are real. But often, the simplest explanation is regression to the mean. The outstanding first season was partly the result of exceptional luck. Balls bouncing the right way, calls going in their favor, minor injuries happening to competitors instead of to them. and that level of luck simply doesn't persist. Their second season is closer to their true average, not because anything went wrong, but because extreme luck is rare by definition. Here's an even more insidious example. Imagine a school district identifies its lowest performing schools and implements a new educational program at those schools. The next year, test scores at those schools improve. Success, the program works. But wait, regression to the mean predicts that the lowest performing schools in any given year will tend to improve the next year, and the highest performing schools will tend to decline, even if absolutely nothing changes. Because some of what made those schools the lowest was random variation, a particularly difficult class of students, a few key teachers having an off year, some disruption in the school community, and that random variation is unlikely to repeat in exactly the same way. So any intervention at the worst schools will appear to work, even if the intervention has zero actual effect. Separating the real impact of an intervention from regression to the mean is one of the fundamental challenges of statistical research, and it's why randomized controlled trials, where you randomly assign some schools to get the program and others to serve as a control group, are so important. Galton's work on regression and correlation. He also developed the concept of correlation, the measure of how strongly two variables are related, laid the groundwork for the field that would become modern statistics. And the person who really built that field into a formal scientific discipline was Carl Pearson. Pearson was born in 1857, studied mathematics at Cambridge, and then went on a remarkable intellectual odyssey through Germany, studying physics, philosophy, and German literature, and even changing the spelling of his first name from Karl to Karl, apparently out of admiration for Karl Marx. He eventually settled at University College London, where he became the first professor of statistics in the world and founded the Biometrica Journal, which is still publishing today. Pearson was passionate, combative, and enormously productive. He formalized the correlation coefficient, the number between -1 and +1 that measures how closely two variables track each other. He developed the chi-squared test, one of the most widely used hypothesis tests in science, which tells you whether the distribution you observed in your data is significantly different from what you'd expect by chance. And he established a philosophical position that shaped science for a century, that the goal of science is not to discover ultimate truth, but to build mathematical models that describe observed data as accurately as possible. The next towering figure in the history of statistics was Ronald Fisher, and Fisher's story is one of the most fascinating and contentious in the annals of science. Born in 1890, Fisher was by many accounts the most important statistician of the 20th century, though you'll find people who argue vigorously for Pearson or for Jerzy Neyman. Fisher was precocious. By his mid-20s, he had already made major contributions to both statistics and genetics, and his 1918 paper on the correlation between relatives essentially reconciled Mendelian genetics with the continuous variation observed in traits like height, laying the foundation for what would become population genetics. Fisher spent many years at Rothamsted Experimental Station, an agricultural research center in Hertfordshire, England, where he developed the statistical techniques needed to draw valid conclusions from messy, real-world data. And the data was messy. Agricultural experiments involve soil that varies from patch to patch, weather that changes unpredictably, seeds that differ individually, dozens of confounding factors that could disguise or mimic the effect of whatever treatment you're testing. Fisher's genius was to develop systematic ways to deal with this messiness. He invented the analysis of variance, ANOVA, which is a technique for decomposing the total variation in a dataset into components attributable to different sources, allowing you to test whether a particular factor has a significant effect even when there are many other sources of variation. He developed the principles of experimental design, randomization, replication, and blocking that are still the gold standard for scientific experiments today. The idea of randomly assigning subjects to treatment and control groups, which seems so obvious now that it's hard to imagine anyone ever doing it differently, was largely Fisher's contribution to science. Before Fisher, experiments were often designed in ways that made them vulnerable to all sorts of confounding biases. After Fisher, there was a systematic framework for doing experiments right, and Fisher introduced the p-value, the concept that has probably caused more arguments, more misunderstandings, and more damage to scientific practice than any other statistical idea. Here's what a p-value is, as simply and clearly as I can state it. You start with a null hypothesis, a default assumption that there's no effect, no difference, nothing interesting going on. You run an experiment and collect data. The p-value is the probability of getting results at least as extreme as what you observed, under the assumption that the null hypothesis is true. If the p-value is very small, conventionally less than 0.05 or 5%, you conclude that your data is unlikely under the null hypothesis, and you reject it. You declare your result statistically significant. Now, this sounds reasonable, and in the right hands, used carefully, it is a useful tool. But the p-value has been the source of staggering amounts of confusion and abuse. For one thing, a p-value of 0.05 does not mean there's a 95% chance your hypothesis is correct. It doesn't tell you the probability that the null hypothesis is true or false. It doesn't tell you the size of the effect you found, or whether that effect matters in practical terms. It's a subtle conditional probability, the probability of the data given the null hypothesis, and people constantly, persistently confuse it with the probability they actually care about, which is the probability of the hypothesis given the data. Notice anything? That's exactly the kind of inversion that Bayes' theorem handles. The confusion between forward probability and inverse probability, the same confusion we talked about with medical tests, shows up right here at the heart of scientific methodology. And the arbitrary threshold of 0.05, which Fisher himself described as merely a convenient benchmark, not a sacred line, has taken on an almost talismanic significance in scientific practice. Researchers speak of achieving significance as if crossing the 0.05 boundary transforms a finding from fiction to fact, when in reality, the difference between a p-value of 0.049 and 0.051 is negligible. This has led to a whole ecosystem of problematic practices, p-hacking, where researchers try different analyses, different subgroups, different variables, until they find a combination that produces a p-value below 0.05. Publication bias, where journals preferentially publish significant results and reject null results, creating a distorted picture of reality in the published literature. And a broader crisis of reproducibility, where many published findings, particularly in psychology and medicine and social science, turn out not to replicate when other researchers try to reproduce them. The p-value, wielded carelessly, has done genuine harm to the practice of science. Now, I don't want to make it sound like the p-value is useless. It's not. It's a tool. And like any tool, its value depends on how it's used. Fisher's contributions to experimental design, to the logic of statistical inference, to the mathematical foundations of genetics, these are immense and lasting. But the story of the p-value is a cautionary tale about what happens when a nuanced, context-dependent statistical concept gets simplified into a mindless ritual. Is the p-value below 0.05? Then it's significant, published. That's not what Fisher intended, and it's not good science, And this brings us to one of the most beautiful moments in the story of probability. The moment when the entire field was placed on a rigorous, unshakable, axiomatic foundation. And the person who did this was a Russian mathematician whose breadth of genius is almost hard to believe. Andrei Nikolaevich Kolmogorov was born in 1903 in Tambov, Russia, and grew up in extraordinary times: the Russian Revolution, the Civil War, the rise and consolidation of the Soviet state. His mother died giving birth to him, and he was raised by his aunt. Despite the upheaval around him, he received a superb mathematical education and showed prodigious talent from an early age. He made his first significant mathematical contribution at the age of 19. By his 30s, he had done foundational work in fields as disparate as topology, logic, turbulence theory, computational complexity, and, of course, probability. He is one of the broadest mathematicians of the 20th century, which is saying something in a century that included people like John von Neumann and Henri Poincaré. In 1933, Kolmogorov published a slim monograph, Grundbegriffe der Wahrscheinlichkeitsrechnung, or Foundations of the Theory of Probability, that did for probability what Euclid's Elements had done for geometry 2,000 years earlier. He took all the intuitive notions about probability, the counting of outcomes, the relative frequencies, the degrees of belief, and grounded them in a simple, rigorous set of axioms using the mathematical language of measure theory. There are 3 axioms, and they're elegant in their simplicity. First, the probability of any event is a non-negative number. Second, the probability of something happening, the probability of the entire sample space, the set of all possible outcomes, is 1. Third, for events that can't happen simultaneously, mutually exclusive events, the probability of at least one of them occurring equals the sum of their individual probabilities. That's it. 3 axioms. And from these 3 spare, simple rules, the entire edifice of probability theory can be constructed. Every theorem we've talked about tonight, the law of large numbers, the central limit theorem, Bayes' theorem, the properties of the normal distribution, all of it can be rigorously derived from Kolmogorov's 3 axioms. It's one of those breathtaking moments in mathematics where a vast, historically messy, philosophically contentious subject gets distilled into a few clean, precise statements from which everything else follows. And here's what's particularly clever about Kolmogorov's approach. His axioms don't say anything about what probability means. They don't take sides in the Bayesian versus frequentist debate. They don't tell you whether probability lives in the world or in the mind. They just provide the mathematical rules that any valid interpretation of probability must follow. It's a framework so general that it accommodates every philosophical position at once, by being strictly agnostic about interpretation and rigorously precise about structure. The Bayesians and the frequentists can argue all they want about what probability is, but whatever it is, it obeys Kolmogorov's axioms. Now, around the same time that Kolmogorov was laying these foundations, probability was finding spectacular practical applications in places that would have astonished Pascal and Fermat. And one of the most dramatic was the Monte Carlo method, a technique that uses random sampling to solve problems that are too complex for any pencil and paper calculation, too tangled for any analytical formula. And the story of how it was invented is, characteristically, a story about people and accident and the unexpected fertility of a simple idea. It's the late 1940s. And a Polish-American mathematician named Stanislaw Ulam is recovering from a serious case of viral encephalitis, a brain inflammation that left him bedridden for weeks. To pass the time during his convalescence, he's playing solitaire, Canfield solitaire, specifically. And as he plays game after game, arranging and rearranging the cards, he starts wondering, What are the actual odds of a given layout working out? What fraction of Canfield deals are winnable? He tries to compute the answer directly, using combinatorics and probability theory, and the calculation is utterly hopeless. There are far too many possible arrangements of a deck of cards, far too many branching decision paths in the game. The problem is, in principle, perfectly well defined, but in practice, analytically intractable. And then Ulam has one of those insights that seems obvious in retrospect, but took a brilliant mind to see in the moment. Instead of trying to calculate the probability exactly, why not just play? Play 100 games, or 1,000, and count how many you win. If you play 1,000 games and win 47, then the probability of winning is approximately 4.7%. You're using random sampling, random simulation, to estimate a quantity that's too complex to compute directly. You're trading mathematical elegance for brute force empiricism, and the law of large numbers guarantees that if you run enough trials, your estimate will converge to the true answer. Ulam mentioned this idea to his colleague at Los Alamos, John von Neumann, and von Neumann immediately grasped its potential. Von Neumann, by the way, is one of those figures who appears in practically every major intellectual story of the 20th century. He was a founding figure in game theory, quantum mechanics, computer science, nuclear weapons design, cellular automata, and mathematical economics. He designed the logical architecture that virtually every modern computer still follows, the von Neumann architecture. He was one of the key scientists on the Manhattan Project, and the stories about his intellectual abilities border on the supernatural. He could multiply 8-digit numbers in his head instantly. He could memorize a column of phone book entries at a glance. He once allegedly translated a passage from ancient Greek while simultaneously carrying on a conversation in English about an unrelated topic. Whether every story about him is literally true, the consensus among his peers, people who were themselves among the smartest on the planet, was that von Neumann operated on a fundamentally different level. Von Neumann took Ulam's solitaire insight and turned it into a practical computational technique, programming it onto one of the first electronic computers, the ENIAC, to run simulations for nuclear weapons calculations at Los Alamos. The calculations in question involved tracking the behavior of neutrons inside a nuclear device, how they scatter, how they're absorbed, how they multiply through fission, problems with so many variables and so many random interactions that exact analytical solutions were impossible. But you could simulate the process. You could trace the path of an imaginary neutron, using random numbers to determine at each step whether it scattered, was absorbed, or caused a fission event, according to the known probabilities. Do this for millions of imaginary neutrons, and you get a statistical picture of how the device will behave. It's not exact, but it's accurate enough to be extraordinarily useful. The name Monte Carlo was suggested by another Los Alamos physicist, Nicholas Metropolis, as a playful code name for the classified technique, a reference to the famous casino in Monaco, because the method is all about randomness and repeated trials. The name stuck, and today, Monte Carlo methods constitute one of the most important families of computational techniques in all of science and engineering. The range of applications is staggering. Climate models use Monte Carlo methods to assess the uncertainty in their projections. Financial institutions use them to estimate the risk of complex investment portfolios. How much could we lose in the worst 5% of scenarios? Drug companies use them to design clinical trials and model the spread of diseases. Engineers use them to analyze the reliability of complex systems. An airplane engine has thousands of components, each with a small probability of failure, and Monte Carlo simulation can estimate the probability that the engine as a whole will function over a given period. Physicists use them to simulate the behavior of subatomic particles in accelerator experiments. Pixar uses them for realistic computer-generated lighting. Each ray of simulated light bounces randomly through a virtual scene, and millions of such rays, averaged together, produce the soft, realistic shadows and colors you see in animated movies. Every time you stream a Pixar film, you're watching the fruits of Monte Carlo simulation. And while we're in the 20th century, talking about the great intellectual contributions to probability and information, we cannot skip Claude Shannon. Shannon was born in 1916 in Petoskey, Michigan, grew up in the small town of Gaylord, and showed early talent for building mechanical and electrical gadgets. He once built a working telegraph system between his house and a friend's house, using barbed wire from their fences as the transmission line. He studied electrical engineering and mathematics at the University of Michigan, and then at MIT, and in 1937, while still a master's student, he wrote a thesis that many consider the most important master's thesis of all time. He showed that Boolean algebra, the logic of true and false, and or, and not, could be implemented using electrical relay circuits, establishing the theoretical foundation for digital circuit design and, by extension, for every computer that has ever been built. But Shannon's most transformative contribution came a decade later, while he was working at Bell Telephone Laboratories. In 1948, he published a paper titled A Mathematical Theory of Communication that essentially created the field of information theory, single-handedly, from scratch. And probability is at the absolute heart of what he did. Shannon's key insight was that information and uncertainty are intimately connected. They're two faces of the same phenomenon. The more uncertain you are about something, the more information you receive when you learn the answer. If someone tells you the sun rose this morning, that's barely informative. You were already almost certain it would. But if someone tells you a meteor struck your neighborhood this morning, that's hugely informative. It was deeply unexpected. Shannon formalized this intuition by defining a quantity he called entropy, borrowing the word from thermodynamics, because the mathematical form of his equation was identical to the entropy formulas of statistical mechanics. Shannon's entropy measures the average amount of information, or equivalently, the average amount of surprise, associated with a random variable. And here's the formula, which is worth understanding even if you're not a mathematician. If an event has probability p, its contribution to the entropy is negative p times the logarithm of p. Sum this over all possible events, and you get the total entropy of the system. The formula has beautiful properties. When one outcome is certain, probability 1, the entropy is 0. There's no uncertainty, so there's no information to gain. When all outcomes are equally likely, maximum uncertainty, the entropy is maximized, and everything in between scales smoothly and intuitively. Shannon used this framework to prove theorems that set absolute, inviolable limits on communication. His source coding theorem says you can compress a message down to its entropy, to the minimum number of bits needed to represent its information content, and no further. Every compression algorithm you've ever used, zip files, MP3 audio, JPEG images, streaming video codecs, is trying to approach this theoretical limit, and Shannon's channel coding theorem tells you the maximum rate at which you can reliably transmit information over a noisy channel, a channel where bits occasionally get flipped or lost. That maximum rate is called the channel capacity, and it depends on the probability of errors in the channel. Below that rate, reliable communication is possible. Above it, errors are inevitable. It's a hard, mathematical wall, and no amount of clever engineering can push past it. The impact of Shannon's work on the modern world is difficult to overstate. The entire digital communication infrastructure, every phone call, every email, every text message, every streaming video, every financial transaction, every web page, is built on Shannon's information theory. The error-correcting codes that keep your data intact when it's transmitted over imperfect channels. The compression algorithms that let your phone store thousands of songs in a device that fits in your pocket. The encryption protocols that protect your bank account when you shop online. All of this traces back to Shannon's probabilistic framework. He showed that randomness and information are deeply, fundamentally intertwined, that the mathematics of uncertainty is also the mathematics of communication, of knowledge, of meaning itself. Shannon, incidentally, was one of the most playful scientists who ever lived. He rode unicycles through the hallways of Bell Labs. He built a mechanical mouse that could solve mazes. He built a machine whose only purpose was to turn itself off. You'd flip the switch, a hand would emerge from inside the box, flip the switch back, and the machine would stop. He juggled. He played chess. He approached the deepest questions in information science with a lightness and humor that's almost impossible not to love. He died in 2001, after several years of Alzheimer's disease, which is a cruel fate for a mind that had done so much to illuminate the nature of information itself. And here, at the intersection of probability and fundamental physics, we arrive at something that would have astonished every thinker we've talked about tonight. Because in the 20th century, physicists discovered something that changed the meaning of probability itself. They discovered that probability isn't just a tool for coping with our ignorance of the world. It's woven into the very fabric of reality. And that discovery came from quantum mechanics. In classical physics, the physics of Newton and Laplace and everyone before them, the universe is deterministic. If you know the exact state of a system at one moment, its entire future is fixed. Probability enters only because of practical limitations. We can't measure positions and velocities precisely enough. We can't track all the variables. So we use probability as a crutch, a concession to our own inadequacy. Laplace's demon, remember, would have no need for probability. It would know everything, predict everything. Probability, in the classical view, is epistemological. It's about what we know, not about what exists. Quantum mechanics says otherwise. According to quantum theory, certain physical quantities are not merely unknown, they are fundamentally indeterminate. An electron doesn't have a definite position until you measure it. Before measurement, it exists in what physicists call a superposition, a cloud of possibilities, each with an associated probability. The probability is computed from something called the wave function, specifically from the square of the wave function's magnitude. When you measure the electron's position, you get a specific result. But which specific result you get is genuinely random, governed by the probabilities that quantum mechanics prescribes. Not random because you don't know enough. Random in principle. Random all the way down. Einstein, as you might recall from his famous remark, hated this. God does not play dice with the universe, he reportedly said. He believed that quantum mechanics was incomplete, that there had to be some deeper, deterministic layer of reality underneath the probabilistic surface, hidden variables that we just hadn't found yet. He spent decades trying to construct arguments against the completeness of quantum mechanics, culminating in the famous Einstein-Podolsky-Rosen paradox of 1935. But in 1964, a physicist named John Bell proved a theorem that made it possible to distinguish, experimentally, between a universe with hidden variables and one with genuine quantum randomness. And starting in the 1980s, with the experiments of Alain Aspect and others, the tests were carried out. And quantum mechanics won. Every time. The universe really does play dice, at least at the quantum level. The probabilities aren't a reflection of our ignorance. They're a feature of reality itself. Nature is, at its most fundamental level, genuinely stochastic. Think about what that means. Every radioactive atom in the universe has a certain probability of decaying in the next second, and whether it actually does or doesn't is not determined by anything, not by any hidden mechanism, not by any deeper cause, not by any secret variable. It just happens, or it doesn't, according to the probabilities. The click of a Geiger counter detecting a radioactive decay is, as far as physics can tell, the sound of a genuinely random event. There is nothing at all, no matter how deeply you look, that determines in advance whether that click will come now, or a millisecond from now, or a second from now. The probability is all there is. And yet, and here's the beautiful paradox at the heart of all of this, that fundamental randomness gives rise, through the law of large numbers and the central limit theorem and everything else we've explored tonight, to the stable, predictable, orderly world we experience every day. The table beside your bed isn't jiggling with quantum uncertainty, even though every atom in it is a buzzing cloud of probabilistic quantum states. The probabilities are so sharply peaked, so overwhelmingly concentrated around certain values, that the quantum randomness washes out completely at the macroscopic scale. The law of large numbers, operating across trillions upon trillions of atoms, turns quantum chaos into classical order. Randomness at the smallest scale, stability at the scale where you live, and the bridge between them is probability theory. Let me bring this all the way home now, because probability isn't just a subject for physicists and mathematicians and statisticians. It shapes your life, right now, in ways you might not think about. When you check the weather forecast and it says there's a 30% chance of rain tomorrow, what does that mean? It means that the weather model has run many simulations, sometimes hundreds or thousands of them, each starting with slightly different initial conditions, because the current state of the atmosphere can never be measured with perfect precision. About 30% of those simulations produce rain at your location. It's not saying that 30% of the area will get rain, or that it will rain for 30% of the day. It's saying that in the space of probable futures, roughly 3 out of 10 include rain where you are. Understanding that correctly helps you make a better decision about whether to carry an umbrella. When you buy insurance, car insurance, health insurance, home insurance, you're participating in a probabilistic system, even if you don't think of it that way. You're paying a certain premium to protect yourself against an uncertain but potentially costly event. The insurance company, on the other side, knows the probability that someone with your profile will file a claim. They set the premium so that, across all their customers, thousands or millions of them, the premiums they collect exceed the claims they pay out. The law of large numbers working in their favor, exactly the way it works for a casino. Individual outcomes are unpredictable. Aggregate outcomes are highly predictable. Insurance is, at its mathematical core, a probability business, and the entire industry, trillions of dollars globally, rests on the same foundations that Pascal and Fermat laid down in their letters nearly 400 years ago. And then there's machine learning, the technology that increasingly shapes what you see, hear, and read in the digital world. At its heart, machine learning is applied probability on a scale that would boggle the minds of the founders of the field. A spam filter calculates the probability that an email is spam given the words it contains. That's Bayes' theorem, applied automatically, millions of times a day. A recommendation system estimates the probability that you'll enjoy a particular song or movie, given your past behavior and the behavior of millions of other users. A large language model, the kind of AI system that generates text, answers questions, and holds conversations, works by predicting the probability distribution over the next word in a sequence, given all the words that came before it. Each word it generates is selected from a probability distribution. The entire revolution in artificial intelligence, that's reshaping our world right now is, at its mathematical heart, an exercise in probability. And you know, lying here thinking about all of this, there's something that strikes me about the arc of this whole story. It started with dice, with gamblers in smoky rooms, rolling bones and knuckle bones, trying to figure out the odds. A brilliant, troubled doctor in 16th century Italy, scribbling the first rules of chance between gambling binges. Two French geniuses, exchanging letters about how to split a card game pot fairly. A quiet English minister, working out an obscure theorem about inverse probability in his study in Tunbridge Wells. That's where probability began, with gambling, with puzzles, with curiosity about the patterns hiding in randomness. And look where it ended up, in the foundations of physics, woven into the fabric of quantum reality. In the infrastructure of the modern world, communication networks, financial systems, medical testing, artificial intelligence, in the way we understand knowledge itself, Bayesian reasoning, statistical inference, the philosophy of science, in the way we build bridges and test drugs and forecast storms and land spacecraft. A branch of mathematics born from gambling has become one of the most profound and far-reaching intellectual achievements in human history. And the philosophical question at the heart of it all, what probability actually is, what it means, remains beautifully, stubbornly unsettled. Is probability a feature of the physical world, as quantum mechanics seems to insist? Is it a measure of human ignorance, as Laplace believed? Is it a degree of rational belief, as the Bayesians argue? Is it a long-run frequency of repeatable events, as the frequentists maintain? Or is it somehow all of these at once, different facets of the same crystal, different ways of looking at the same deep truth? Smart people disagree passionately, and have for centuries, and probably will for centuries more. And that's genuinely okay. The mathematics works regardless of which interpretation you prefer, just as Kolmogorov intended. The axioms don't care what you think probability means. They just provide the rules for working with it. And those rules, applied with care and understanding, give us extraordinary power to navigate an uncertain world. Because that's the thing about uncertainty. It's not something to be afraid of. It's not a failure of knowledge or a gap in understanding. It's a fundamental condition of existence. The future is uncertain. Outcomes are uncertain. Even the present is uncertain, if you look closely enough, down at the quantum level, where electrons shimmer in probability clouds and photons take every possible path simultaneously. Uncertainty is the natural state of the universe, and probability is our way of making peace with it, of working with it instead of against it, of finding the patterns hiding inside the noise, the signal buried in the static, the reliable truths concealed within the chaos. And maybe that's the most comforting thought to carry into sleep tonight. You don't need to know what happens next. Nobody does. Not the physicists, not the statisticians, not Laplace's demon. But you can reason about what's likely. You can prepare for the probable, hedge against the improbable, and accept, with grace, even with wonder, that some things are genuinely, irreducibly uncertain. The mathematics of chance, this beautiful, deep, endlessly surprising subject that grew from a gambler's question in a 17th century letter, it doesn't eliminate uncertainty. It dignifies it. It gives it structure and shape. It shows that even in a world where you can't predict the next roll of the dice, there are patterns underneath the randomness, stable truths about the behavior of chance, elegant forms that emerge from chaos if you step back far enough to see them. The bell curve is there, whether you notice it or not. The law of large numbers is running, right now, across every random process in the universe, smoothing noise into signal, turning unpredictability into pattern. Bayes' theorem is the quiet logic behind every time you update what you believe in light of something you've learned, whether you do it consciously or not. These aren't just abstractions on a mathematician's chalkboard. They're the hidden architecture of the world you live in, the invisible framework holding up every forecast, every diagnosis, every decision made under the permanent, pervasive, perfectly natural condition of not knowing for sure. So let that settle now. Let the numbers fade. Let Pascal and Fermat and Bernoulli and Bayes and Kolmogorov and Shannon drift gently into the background, their work done, their legacy alive in every weather forecast, every medical test, every message that arrives intact across a noisy channel, every quiet click of a GPS satellite finding your position to within a few meters of where you actually are. The universe is uncertain, and always has been, and always will be, but it's uncertain in ways that are beautiful and structured, and, with enough patience and enough care, deeply understandable. That's what probability teaches us, not certainty, something better than certainty, a way to think clearly when the outcome is unknown, a way to live wisely with uncertainty. And right now, the most probable thing in the world is that your breathing is slowing, your thoughts are softening, and sleep is drawing very close. The odds are in your favor. Let them carry you, gently and reliably, into the night.